So we will take up analysis of rigid plane frame by flexibility method. Of course, the steps involved in analysis of even plane frames also similar to what we have done in the same 4 steps. First step, you have to find the degree of static indeterminacy and make the structure determinate by introducing suitable releases. Then end with suitable coordinates. Then second step, to find out the displacements along those coordinates chosen by using standard formula or by dummy load method, whichever is required depending upon the situation. Then third step, you have to generate flexibility matrix. Then fourth step, use your force displacement relationship to determine the unknown retardants. Those 4 steps remain same even in this analysis of rigid plane frames also. Now let us start with the analysis by taking up a problem straight away. So let us take a rigid plane frame structure as shown in this particular figure. Let us take a 6 meter rigid plane frame, 6 meter by 6 meter rigid rectangular orthogonal frame of flexural rigidity 2 EI for 2 members, EI for another, and 6 meter is height for all this. So subjected to a UDN along the beam of intensity 50 kilonewton per meter along with a lateral load of 20 kilonewtons acting from right to left at point C. So this is the problem we are taking in this particular case. So first step, as usual, find the degree of indeterminacy. Of course, I told you they are all externally indeterminate, all single story rigid plane frames. They are also externally indeterminate to the degree either 1, 2 or 3 maximum, similar to beams. Here also, since there are 2 fixed ends, so degree of external indeterminacy has to be 3. Straight away you can judge. Then you make the structure determinate by introducing 3 releases in the form of external support reactions. So there are various ways. One way is to make this hinge, this roller. Thereby I can remove one moment here, here one moment, and horizontal reaction. Second way, straight away I can remove either support D or support A. Thereby all the 3 reactions can be removed. So let us go for the second alternative, that is, so make the structure determinate. Make the structure determinate by making the end joint D free as in figure. So I make this structure determinate in this fashion. So when I make this end free, I have removed 3 support reactions. Those some reactions which have been removed, I will indicate it by coordinates like this, 3 coordinates. 1 horizontal reaction, 2 vertical reaction, and 3 moment. All these 3 reactions we have removed at D. 3 releases I have introduced. Here, this is HD I have removed, this is BD I have removed, here some moment MD I have removed. So therefore, the releases which you have made are R equals HD, VD and MD along these 3 coordinates. This indicates the positive direction of these forces. HD is from left to right, VD from bottom to top, and MD is anti-clockwise. This is the coordinate directions I have assumed to start with. This is that we have to determine during our analysis. And now this is subjected to external loading like this, since I have removed these three reactions. And these three reactions earlier, there was no displacement occurring because it was fixed. But now since I have removed that, displacement will occur. This is called inconsistency in deformation. Inconsistency is introduced. I am introducing inconsistency now in order to make it determinate. That inconsistency in displacement I have to evaluate. That is, I have to evaluate that inconsistency in the deformation due to external loads along the coordinates 1, 2 and 3. Due to external loads, I have to determine. That is from our usual conventional methods like dummy load method. Here we have to adopt dummy load method or strain energy method. And then any support settlement, if at all it is given. Secondary thing, that also I have to take it here itself. Here no secondary effect has been given along these redundant forces, so this dr will be 0. Therefore, this net displacement, which is nothing but dr minus dl, which is just minus dl1 minus dl2 minus dl3. These dls we have to determine. That is our next second step. Second step, to find this d, and c. D itself is that dl now. That d I have to evaluate all the displacements. So it is nothing but a problem on displacements. So which you have studied in previous semester, I have altogether in 2 units. Those 2 units you have to remember. First unit, just by finding simply supported beam displacement, which already I have used in analysis of the ready-made formula. Next, strain energy method of adopting, evaluating the displacement by applying Castaneda's theorem. So that we are using here now for finding this dl. Now straight away we will adopt that strain energy method or dummy load method for evaluating this displacement. So we know that d is equal to sigma of integral dx divided by L. It is the formula we have. Displacement along any coordinate is given by that formula. Where M is the bending moment at any section of the members of the given structure. Small m is the bending moment due to those section itself due to unit load applied along the same coordinate, whatever, where we have to determine the deflection. That you know already. I need not explain those things. Straight away here I will do the calculation. So this, just remember, we have d along any coordinate is given by this formula. So where m is the bending moment due to external loading on the basic determinate structure. The external loading of this is 20 kilonewtons, 50 kilonewton per meter, A, B, C, D. So in this member, I have to take up a section x1 at a distance x from the lower point D. So whatever moment I have taken about this section, that holds good between D to C, because there is no other load which is causing the variation of that moment. So one section is enough for this particular member for evaluating M, capital M due to external load. Then another section I will take in this member x2 at a distance x from this point. So whatever moment I have, the same moment will be there right from point C to point B in the B. Same moment it has to be. There is no other variation. So this section, I will take moment about this section. That same moment holds good for this entire portion. So CD over, CB over. Next I will take up another section X3 at a distance X either from point A or point B in the member AB. So here also whatever moment I am taking at this section X3, it holds good from A to B. So thereby I have covered the entire section by taking 3 sections for evaluating this MX. So I will integrate it from one point to another point. From first point to last point, first point to last point, I will get this M. That's what it is there. So that the entire structure has been covered. Then this small m is the unit load I have to apply. I have to evaluate the displacement along each of the coordinate 1, 2 and 3. I have to apply unit load along those 3 coordinates. So I will have to apply a unit load here and same sections I have to take x1, x2, x3 for calculating this m to cover the entire structure. This is for calculation of m, this is for calculation of small m1 along that one. Next, I have to apply unit load along the coordinate 2, that is in the direction of coordinate 2, I have to apply unit load. And again, I have to evaluate that small mx2 at these sections only. So it covers the entire structure. I have to find out due to this load, what is the moment? Due to this load, what is the moment? This is to be given external load. Then for finding out DL1, I have to use M1. For finding DL2, I have to use M2. For finding DL3, M3. That's all the procedure we are following in dummy load or unit load method of finding the displacement. Next, I have to apply unit load along direction of the coordinate 3. And again, I have to evaluate the moments along these same 3 sections. This is what I have to do first. All these I will calculate it in the form of, I will just evaluate in the form of a table. So that is very convenient. For there are 3 sections. Along those 3 sections, I will calculate the moments calculated. So first I will take range or segment. Range or segment. Range is first from A, B, C, D, everywhere. A, B, C, D. First segment is CD. Next, BC, CD, BC, then D. These 3 elements of the given structure, I will take it. I will find out the moment M due to external load, moment due to unit load in the form of table. Then here, origin. For calculating the distance, I have taken the origin here for measuring the distance. For x1, I have taken the origin as D. So here it is, D is the origin. For BC portion for x2, C. The origin is C. For AB portion, it is A. I have taken the origin. Then the integration limit I will show. For BC portion, it is x is equal to 0 to 6. X is equal to 6 meters. It is 0 to 6. For BC also, it is 0 to 6 because they are all of same length. And for AB also, it is 0 to 6. In this line, so there is no change in the moment, whatever I am going to calculate it. So that straight away those values I can put it here, integrate it, arrive at the displacement. This is the procedure we follow. Next, I will write this M computation, capital M, that is this. So here I will find out the reaction because there is only one support. Here 20 is acting like that. So sigma H equals 0 if I take, here there must be a horizontal reaction 20. Then here total load is 50 into 6, 300. It is acting down. Here there must be equal and opposite load 300 in per direction. Then here moment, because it will support, I have to find the support reactions first. So I will get a moment due to this load 50 into 6, 300 into 3, that is 900 in the clockwise. In addition to that, this load also will give moment here, that is 20 into 6, 120 in the anti-clockwise direction. So this 900 minus 120,
780.
that is acting in the opposite direction like this. Because 900 is this way more, so it should be opposite to that. So this will be 900 minus 120. That is 780 kilonewton meter. This is kilonewton meter. These are the support reactions. Now I will evaluate M, capital M. So for this portion, for this section, I will consider free body diagram towards right. There is no load. So naturally moment about that section is 0. It is 0. Next, for this, I will consider free body diagram towards right side of the whole structure. So the bending moment will be 50 into x into x by 2. That is 50 x squared by 2. That is 25 x squared. That acts like this. Right? So opposite side it will be opposite that. It gives a hogging type of moment. So it is negative. So that is, this is 20 minus 25 x squared. Moment about section x2 is 50 into x into x by 2. That is hogging minus 25 x squared. Then here x3. Due to this, I will consider free body diagram towards this side. So that is, this will not give any moment. This gives hogging moment. This also hogging. So both are negative. So that is minus 20x minus 780. So that's the moment.
So sir, we have to take a moment towards origin. Origin point, we have to consider
about this section. About this section. I have taken the distance x. So 20 into x. That's 780.
For x2, that is
x2 also. Here no load. Only this. This about the section. About the section, not origin. About the section. Because whatever moment is there, that holds good from x equals 0 to x equals 6.
So the sign convention we have to remember for this.
That is usual. In spinality type and told. That's beam sign convention. Load giving sagging type of moment positive, hugging type of moment negative. Same sign convention. Let us follow this. That's all. Next, I have to find out M1, M2, M3. M2, M3. And of course, this portion is EI, this is 2EI, this is 2EI. Because EI is varied, it is not constant. That also we will indicate in that particular table. Now coming to the M1, this on same lines, we have to find out a same section covering the entire structure, the moments, capital M, small m, in order to work out these displacements. So now coming to the M1, same thing, moment about x1, it is 1 into x. it is giving a moment like that inside sagging positivities. So it is 1 into x positive. Then about this section, it is 1 into this height 6. 1 into 6, that also gives sagging type of moment. So it is plus 6. Right? Now here there must be equal and opposite reaction, and sigma v equals 0 will not give anything. Sigma m also will not give anything. Only these are the reaction. Here it is 1 into x, that is again sagging because inside tension, so that's also sagging. 1 into x. So these are the movement. So straight away now I will work out dl1. dl1 is sum. This sum is for all these. This portion, this portion, this portion. Integration over that limits. dl1 is for this first one 0 to 6, 0. Because 0 into m1, 0. Next, plus it is again 0 to 6, 6 into minus 25, that is minus 150 x square dx. Then plus this is also 0 to 6, 1x into this, that is minus 20x minus 780 into dx. Now it is just evaluation of the integral. You should not do any mistake. You should be experts in integration. This you have to integrate it. You get dl1. So this, it is minus 150. This will be x cubed by 3. Integration of x squared dx is x cubed by 3. Limits 6 to 0. Then in here it is minus 20 into integral x dx, that is x squared by 2, limits 6 to 0. Then this is minus 780, integral of dx is x, limits 6 to 0. You substitute this. This is 6 cube, 216, divided by 3, 72. 72 into minus 150.
10,800.
10,800. Of course, this is by year, and 2 year, because in the formula, for this portion it is
2 year.
2 year for this.
2 year.
So this by 2 year. Then here it is 6 square, 36 divided by 2, 18. 18 divided by 2, 9. 9 into minus 20, it is minus 180 by year. Here also you can take it as 5,400. Here it is minus 180. And here it is 6. 6 divided by 2, 3. 3 into 780.
2340.
2340 divided by
year.
Now you can sum up this. That is your dl1. 5,400 minus 180 minus 2340.
7920.
7920 minus divided by
year.
This is your dl1, whatever we need here. And next, dl2 on same lines. I have to work out m2. m2 means this figure. This is 1 upward. Here it should be 1 down. Right? This gives a moment, because this is not in equilibrium now. This gives a moment in this direction, that is 1 into 6. Right? 1 into 6 in the anti-clockwise direction. So here there must be a moment in the clockwise direction, that is 6. Is it clear? Now this is in equilibrium. This is also in equilibrium. This is also in equilibrium. That you have to make sure. With all free body diagrams, it has to be in equilibrium. So horizontal is not at all there. Now you can evaluate again. M2 for this portion. This is only low towards right. That will not give any moment. 0. Then here, this 1 into x. 1 into this distance x. It is second type of
Positive.
moment, so it is positive 1x. Now when you come to this 6 is there, 6, and this will not give any moment, so it is just 6.
So for that section, we don't consider that particular right side 1 unit vertical load.
Which one? This is
right side one, point D. For that section.
If you make this determinant by making hinge and roller, you have to take that. Usual. There also have to find the reaction, whatever is coming, that you take it. That's the thing. That's the usual procedure. Fundamental procedure of evaluating, because this is determinant structure.
No, so
you have to first find.
The thing is, when we are considering x2, we consider the point D 1 unit.
Which one? Point
For
D?
x2, 1 into x. The reaction.
Well, here.
X to x.
Here I do. This is that I have indicated here. Origin I have mentioned. From there x is measured for this portion, CD portion. X is always measured from this origin. For this, x is measured from that. So from there you, up to this section, whatever distance is there, that you take sign convention also moment. That also you see as per that. Nothing other than that. Right? This already you have done lots of problems, strain energy. So same thing and to follow. Nothing other than that. So
at AB only 6 we have to consider.
Here.
Only
this
moment.
Is only moment. This moment remains same. And because this is vertical reaction.
0.
So it will not give, it passes through that section. It will not give any moment. Moment you will get only when there is lever arm like thing. It is not there at all. Along the line of action of force, it will not be at some distance.
So we are considering only the span AB.
AB only.
AB only. But when we come to CB span,
CB,
BC, horizontal.
This horizontal.
No, second one BC, horizontal, X2, section X2.
This.
Yes, sir, X2. We consider 1 unit because of.
Now it is here.
Yes, sir. The 1 unit is also acting at C.
You have to see the line of action of the force and the section. If it is not coinciding, had this section and would have been here, like this,
yes,
I would have taken anything moment. That's it. That's the basic applied mechanics.
Transmission.
Semester 1.
Yes, sir.
Knowledge.
You have to see C to B, D to C, it will pass 1 kilometer.
Yes. CD, it passes.
Yes, sir.
Whereas here it will get, you will get, that's what you will see by computing this M3.
Yes, sir.
That this is coming into picture. Only one will be there.
Yes.
That I have to consider there. That one, it will be acting.
Yes, sir.
For that portion. Whereas here 0, here only we get M1, 1 into x. Only horizontal reaction and movement.
Yes.
They are active for that portion CD. Okay, DL2 on same lines. DL2 is MM2. First one is 0.
0.
Next, this.
Minus 25.
Integral, of course, plus 1 over 2EI. Integral, because this is 2EI, integral 0 to 6. It is minus 25x squared into x. It is minus 25 x cubed dx. Then plus 1 over 2EI. Integral this 0 to 6, this into this, 6 into
2
minus 20, that is minus 120 x, then minus 6 into 780.
4680.
4680. This into dx. That's all.
So 4680 into x, sir.
Where is
To
x?
multiplied by x.
Where is x?
6. Okay, sir.
It's only this much.
Yes,
No,
yes.
yes. You have to do it correctly without any mistake.
Yes,
It is just integration.
Yes, sir.
So this will be 1 over 2ei. That is why in beam problem I use straight away the ready-made formula. I didn't apply unit load. Here there is no question. You have to go for unit load method.
Yes, sir.
There is no other go. So this is 1 over 2ei. Then this minus 25 into integral of x cube dx. It is x4 by 4 by 4. Then here plus, not plus, minus 120
X square.
into x dx is x squared by 2, limits 6 to 0, and this is minus 4680 into dx. dx is x, limits 6 to 0. You have to evaluate now. This is the, because for both 1 over 2ei I have taken outside, I got that. So this is 1 over 2ei into this, again limit 6 to 0. This is 6 to the power of 4 divided by 4.
Minus 8100.
And into 25.
Yes, sir. Minus 8100.
Minus
8100.
8100. 00. 8100. Here it is 6 square 36. 36 by 2 18. 18 into 120.
Minus 2160.
2160. Then here it is 6. 6 into 4 6. 80. That is
28,080. 28. 28.
38.
28.
28.
1008. Yes, sir. Right, sir.
Okay. So now we can sum up this divided by 2ei. That is your dl2.
19,170.
Okay, minus
Minus 19,180.
19,180.
170.
170
Divided by A.
divided by ei. And lastly, dl3. dl3, you have to see this figure. Already I have written the for CD. It is 1. For this, again it is 1 only.
Yes, sir.
Then for this, since it is 1 here like this, here it will be 1 in the opposite direction. And about x3, this is also 1 only you are getting. So all these are 1. So you can evaluate DL3. DL3. So this is the behavior exercise, what you have done in previous semester. DL3 is, again from this table, it is MM3. MM3 I have to take. MM3 is 0 into 1, 0. Then it is only 1 over 2ei. I will take it for both. So integral 0 to 6. 1 over 2ei 0 to 6. This into this. It is 25x squared into 1. So it is minus 25x squared dx plus 0 to 6. This into 1. So it is same as this. So that is minus 20x minus 780 dx. Okay?
Yes, sir.
Is it minus 20x? Yes.
Minus 20x, sir.
So this is that dl3. This you can simplify. It is equal to 1 over 2ei. It is minus 25 x cubed by 3 limits 6 to 0. Then minus 20 into integral x dx. It is x squared by 2 limits 6 to 0. Here it is minus 780 integral dx. It is x limits 6 to 0. So this simplified 1 over 2ei. This is 6 cubed, 216 divided by 3, 72. 72 into minus 25.
1,800.
1800. So this is 6 square 36 by 2. 18 into 20, 360. This is 6 into 7, 80. 4680. Now we can sum up this divided by 2. That is the displacement along that coordinate 3.
3420 minus 3420.
3420 by L. Therefore, my D matrix is equal to D matrix is minus DL1 minus DL2 minus DL3. I have calculated DL1, DL2, DL3. So I will take 1 over EI outside. DL1 is 7920. Because minus of minus, it becomes plus. Here it is 19170. Here it is 3420. This is your second step in the analysis. This step is that. So this is that we have to calculate the second step. To find D, I have evaluated D. This much exercise from that. Next, third important step is evaluation of flexibility matrix. For that again, I need this table. So next, third step, all these things I can take it out because I have evaluated D. So next, third step, we find flexibility matrix. Flexibility matrix F. Here there are 3 coordinates. So size of flexibility matrix is 3 by 3. So the flexibility matrix you can write it as F11, F12, F13, F21, F22, F23, 31, 32, 33. So totally 9 elements you have to evaluate. Straight away here I will give you the formula that Fij is given by Fia is given by sigma of m1 mi square dx. Integral mi you have here, small mi. Unit load you have to apply, unit force you have to apply, find the displacement. That's why I told you the table we have to adopt the dummy load method only. Any Fii, similarly F22 is sigma m2 square, F33 m3 square. All these diagonal elements you can find out by taking square of that unit load matrix, whatever you have done. Then this, it is product, that is Fij, you can work out as sigma of integral mi mj dx. That is, if you want m12, f12, this is m1, m2. If you want f23, it is m2, m3. If you want m13, f13, m3, m1. That's all. This you have to remember. So how to generate flexibility coefficients and how to evaluate displacement. These are the only 2 exercises, major exercise, which is nothing but strain energy method of finding the displacement. Then you have to use force displacement relationship for finding the evaluation. Now I will find out first F11. This you can say we have this coefficient Fia is given by this. So F11 is nothing but sigma of integral m1 square dx. That is nothing but, you take here, m1 square dx.
X square.
For this form, it is 0 for the entire structure again. It is nothing but 1 over EI integral 0 to 6 of x square dx. Then plus 1 over 2 EI integral 0 to 6 of 6 square, that is 36. Then plus 1 over 2ei integral 0 to 6
X.
of again x square dx. So this you have to evaluate. This is, I will take this 1 over 2ei outside fully. This I will multiply by 2. That's all. Right? So this 2 into integral x square dx is x cube by 3. Limits 6 to 0. These two I have taken outside. So it's same thing. Plus here it is 36 into integral dx. Yes, 60. Then this is integral 1 over 2 here I have taken outside. This is x cube by 3. Limits 6 to 0. This you can simplify. So this is 1 over 2ei is 6 cube 216 divided by 3 72 and into 2
144.
that is 144. Then here 6 into 36 216. Here it is 6 cube 216 divided by 3 that is 72. This sum
432.
432
divided by 2.
divided by 2.
216.
6 divided by n. It is your F11. Then F22. F22 on similar lines. It is sigma of m2 square dx by ei. So m2 square you have to find out. This it is 0. Only these two. 1 over 2ei. I will take it outside. So that is x square integral 0 to 6 x square dx plus 0 to 6. That is 6 square.
36.
That is 36 dx. This you can simplify. It is 1 over 2ei into this is x cube by 3. X cube by 3 means 216 divided by 3 72.
72.
This is 72. Here it is 36 into x. X is 6. 36 into 6. 216. This is 216 plus 72.
288.
280 divided by 2.
144.
And
144.
144 by ei. This is your F22. Like that you can find out other elements. Then you will have F. So F33 is equal to M3 square. All are there. 1. So I will take 1 over 2ei outside because here I will multiply by 2 for the first one.
Yes, sir.
2 into integral 0 to 6 of 1 into 0. Not 1 into 0, 1 only.
1 into dx.
1 dx. This you have to be careful because I have taken
Yes, sir. 2ei outside.
And plus there again it is 0 to 6.
1 into dx.
1 dx plus 0 to 6 1 dx. That's all are 1. So this will be 1 over 2ei. This is x into 6. 6 into 2, 12. Then
6.
here it is 6. Here also 6. It is 24 by 2. It is 12. Right?
Yes, sir.
12 by ei. This is your F33. Then F12, that is nothing but F21. They are equal because always this is symmetric. F12 is F21. So I have to take sigma of M1, M2. This formula I have used. So it is M1, M2. First one is 0. That is 1 over 2ei into second one, it is 0 to 6. M1, M2, 6 into 1x, it is 6x dx plus M1, M2, 1x into 1, that's again 0 to 6 x dx.
Sir, 1 into 6.
M1, M2, 1 into 6. 6 dx.
6x.
So this is 1 over 2 EI. This is x squared by 2, 36 by 2, 18 into 6, 108. This is 6x.
Sir, that is 6x. Sir, that is also 6x, sir.
Which one?
0 to 6. 6 into x.
M1,
Yes, sir.
M2, 6x. Okay, that's also 108.
8.
So this is 216 by 2, that is 108
by EI.
Then F23 equals F32 equals F23. Here again first one is 0, only this, that is 1 over 2 EI into 0 to 6, 2, 3, 1x into 1, that is x dx plus 0 to 6, 6 into 1, 6 dx, that's all. So this is nothing but 1 over 2 EI, this is x squared by 2, 36 by 2, 18. This is 6 into x is 6, 36. 36 plus 18, 54 by 2, it is 27 divided by EI. Then lastly, F13, F31 are equal F13, that is this into this. First one, all are coming into picture, that is 1 over 2 EI, I will take it outside as usual.
2 into.
So this I have to multiply by 2.
2 into x.
2 into integral
X.
0 to 6
X into
of x dx, correct?
Yes, sir.
It is 1x into 1, then 6 plus 0 to 6 of 6 dx, then plus third one 0 to 6 of 1x into 1, that is x dx. So this is 1 over 2 EI into, this is x squared by 2, that is 36 by 2, 18 into 2, that is 36. Here it is 6, into x is x is 6,
36.
6 into 6 again 36. Here it is x, integral x is x squared by 2, substitute upper limit 36 by 2, 18. So 72 plus 18.
90.
90 by 2 is 45.
45 by EI.
90 by 2, 45 by
EI.
So I have generated F also. Now we can remove this table. We need not use that. Because for this various steps, second and third, one generation of displacement D, another generation of flexibility. For full, we were free. Full independency I have taken. Therefore, F is equal to, I will write here. F is equal to. So I will take 1 over EI outside and all these. And any other thing common, can I take?
No, sir. 12. No, sir. 45.
No other thing? Okay, that means
45.
I think 3 I can take.
Yes, sir.
Huh?
Yes, sir.
3 I can take it outside. 3 divided by EI. So F11, 216. 3 I have taken outside. So this will be 72.
72.
Then F12. F12 is 108. 3 I have taken outside. 36. Then F13, 45, 3 I have taken outside, so it is 15. So this has to be 36, 15 because it has to be symmetric. F22 is this 144, 3 I have taken outside, 48. Then F23 is here, 27, I have taken 3 outside, so this is 9. Then lastly, F33, it is 12, 3 I have taken outside, 4, so it is 4. That is my flexibility matrix. This much exercise, which is nothing but largely integration and your dummy load method of preparing thing. Both you should have the prerequisite of previous class courses, that is applied mechanics, all those things. Your strain energy method, all you have to remember. Then last step, fourth step, to find these hard redundant force. So you use the force displacement relationship. We have B is equal to F into R. Do I have evaluated? Yes, I have evaluated. R I have to find out. Therefore, R is equal to F inverse D. So R is nothing but my HD, therefore HD, BD and MD equals F inverse. So you have to find out that. So that is 3 by EI, it becomes EI by 3. Then you have to evaluate this determinant. So the determinant delta is nothing but this 72 into 48 into 4 minus 9 into 9. 192, 48, 4 into 4. Then minus 9 into 9, 81.
So 111.
Then this minus 36 into, because this is plus, this is minus. So minus 36 into 36 into 4, 144. Minus 9 into 15, 135. That is that. Then on this 15 plus 15 into 72 into 48 minus 36 square. How much is that? 72 into 48 minus 36 square.
72
into 48.
3456. 3456
minus 36 square.
36 square. 2160.
Final answer?
Yes, sir. 2160.
2160. So this you have to evaluate. 192 minus 81. That is
sir, total determinant is 24, 73, 2.
1 over 20.
24, 73, 2.
7.
3, 2.
3, 2. This is my determinant. 1 over delta. Now cofactor of this and transpose. Because now it is symmetric, the transpose remains same. It doesn't matter. So it is 48 into 4 minus 9 into 9. 111. 111. Then minus this 9. 36 into 4 minus 9 into 15.
Minus 9 into 15. So we are getting 9.
9. That minus, of course. Then this 36 into 9 minus 15 into 48, that is
minus 396.
minus
396.
392.
396.
6, sir?
Sir.
Okay. Minus 9 minus 396. Then this element 72 into 4 minus 15 square.
63.
16, huh?
63. 63.
63. Then this is minus, of course. 72 into 9 minus 15 into 36.
108.
Huh?
108. 108.
Minus or?
Yes, sir. Minus.
Minus. Then last element is 72 into 48 minus 36 square. That is my inverse.
2160.
2160.
60.
This into D. D you have got here. That is 1 over EI 792019170340. So this is 3 by 3, this is 3 by 1, resulting will be a 3 by 1 matrix. This 1 over here will go. This into this, minus this into this, then this into this, divided by this. And to do it, so you get that is 3 by 1. You will get HDVD. I think, let me check out that result. I don't know. So as per my calculation, this will get 13.4, this 138.9 and 22.6. You will not just check this one, that is your result. Finally, you have to plot bending moment diagram.
Sir.
So another 5 minutes I'll take, I'll close it. So after evaluating this, so I can plot bending moment, shear force diagram. How much you got? Correct?
Yes, sir.
If it is correct, I am happy. So this is A, B, C, D. Now I got, this is minus 13.4. Minus means whatever direction I had assumed to start with. I have taken like this, so that should be reversed. So this is 13.4 kilonewtons. So this is 138.9, and this is like this. I have taken 22.6 kilonewton meter. These are the things which I got at this satellite. Now I have load here 50 kilonewton per meter. This another load. I will find out the reaction here. Sigma H is equal to 0 if I apply. This is 13.4, this is 20. So this has to be 33.4 acting this way. It has to. Now sigma V has to be 0, so this is 50 into 6, 300, the 300 minus 138.9. 161.1. So it becomes 161.1 plus 138.9 is equal to that. So then similarly, we can find out this moment. So this is 50 into 6 into 3, that is 900, that is acting in clockwise direction. This is anti-clockwise, that is minus 22.6. Then due to this, because this also will be a moment about A. So this is 138.9 into 6. That is also minus 138.9 into 6.
Total 44.
7.
No, sir. Total 44. Sum. Final moment. Yes, sir. Final moment 44.
So this
44.
44. Okay. This has to be, because this is clockwise, this has to be anti-clockwise. So this has to be 44. These are my final result. Now we can plot bending moment diagram first. So here, this is the reaction 161.1. Here 138.9. The same reaction should be there, and this is that load 50 kilonewton per meter, 6 meters. Okay, and the moment here this is 22.6 anti-clockwise. Here it should be
Clockwise.
and this 13.4 into 4, it is clockwise. 13.4 into 6, 13.4 into 6,
80.4.
80.4
0.4.
minus, this is in the anti-clockwise direction, this also anti-clockwise, correct?
Yes.
No, this is anti-clockwise, this is clockwise, this is anti-clockwise,
Minus
80.4 minus
22.6.
22.6.
57.8.
57.8, correct. That is the moment there. 57.8. On same lines here, 33.4 into 6. 33.4 into 6 plus 44.
244.
240.
4.4. 244.4.
Okay, so that is in the anti-clockwise direction.
Clockwise, it's anti.
This 244.4, whatever it is. So here, this is 244.4. Because this and that, they have to be one and the same. So you know this moment, you can plot this bending moment diagram. This is 57.8. You can cross check this with the earlier results, whatever you got by other method for same problem. So this is fixed moment diagram, superpose free moment diagram, 15 to 6 squared by 8, I think 225.
Yes, sir. 225.
Okay, it comes something slightly less than this. This is 225. So that moment diagram is negative, positive, negative. This is the bending moment diagram in the member PC. And for AC, here you got 244.4, that is this side. Here also it is 44 charge. I don't know whether it is same sign or not. This here, it is this way. Here it is, here also it is 22.4. It is 22.6. So these are the bending moment in column. In AB, this is BMD. In C, this is BMD in BC. That's all. That's the bending moment from that result. So this much again you have to do the calculation from that reaction. So this much work is there. So next class, if possible, we will take one unequal length. That is still complicated and also laborious. Computation work is more. P problems are all very easy. Just think about it. If you don't have any alternative, well, you have to take up this example and waste about 1 hour in the exam also. Yes, go to that.
Thank you, sir.